very clear. Sometimes and there is just couch for person. Every day. It's really
All right, well, it's 12:20, well, it's 12:21, so we will make sure we get started. We've got a couple people on Zoom. We've got maybe a few more showing up in person. We've got 2 groups in person, so that's really good. Can everyone on Zoom hear me if I just leave my little mic box here? I talk with my hands, so holding my mic box is not going to work today. So, well, thank you all for coming and for being here. And my name is Cindy Tran. I am the College of STEM faculty innovator, one of our 2. And I'm excited to share some active learning techniques for the technical classroom. I did not call it a STEM classroom because I feel like there's a lot of technical work in terms of mathematics and diagrams and these things that are not straightforward. I'm going to pose a philosophical question and let's answer it through discussion kinds of topics that we want to do active learning with, but we just don't always know how. My background is in chemistry and forensic science. So what you'll see today is a lot of chemistry examples, and I'll kind of talk you through where we are at different levels, but I hope it's kind of entry level enough that you can kind of get a feel for what we're doing. I am modeling actively today. So there is a handout. If you're on Zoom, make sure you grab it and be ready to chat with each other in the chat box on Zoom or in your groups in person. We will do a little bit of group work so you get a really good feel for how the flow works with some of these things. So why active learning? We'll do a little bit of background and then we'll dive right into some actual active learning materials. So active learning is, I changed it on my computer, but not, there we go. Active learning is just any instructional method that engages students in the learning process. And we're going to focus in the classroom, I think, especially in some of the fields that we work in that may have a lab associated with it. The lab, we're like all about the experiential learning process there. And we're like, well, in lecture, I'm just going to throw information at you and you're just going to have it for when you need it for that lab stuff. But I think we can do more experiential learning in the classroom and that'll really help students when they get to lab or other types of big problems in their field. So today we're going to look at experiential learning, and we want active learning because of the development of some additional learning outcomes. This is something that I really love about active learning in my classroom is I make students work in teams. They must problem solve in front of me. I know they're doing it. They aren't just Googling. There's some leadership, in group discussions and in group projects and in group work, there's usually people that kind of emerge in leaders, but also ways in which you can kind of force students that don't normally take a leadership role to take a little bit of that experience. And I love that they have to express and defend their thoughts. It drives me nuts when we talk about the skills we want our graduates to have. We want them to be able to sit at a table and discuss their thoughts on the fly and reason through things. And we never do that in class. So this is my way of forcing that into my class. There's been some good studies about inclusivity and higher retention of our kind of underrepresented minorities. And we know that a lot of students that come into EKU are from underrepresented minorities, first-gen households. And so if we can build in things that give us higher retention rates by showing them they have a seat at the table and that they have a place here, then I think we do them a great service. Why our technical classroom, as I kind of said, we do a lot of throwing information at students. And active learning has been around for a long time, but implementation into STEM fields and more technical fields has been quite slow comparatively to our social sciences and some of our humanities side of the campus. And these are some of the kind of quotes I've said as an early faculty, or I have heard from other faculty in my discipline or other kind of technical disciplines. And I want to say I kind of came by this when I started teaching. I knew I wanted student engagement and interaction. I didn't know how to get it. I knew I didn't want to hear myself talk for an hour and 15 minutes every time I lectured, but I didn't know how to get there into having more students. And my chair in my first year was like, hey, there's this workshop. And it was a 1-week immersive workshop for my field in analytical chemistry where people that had been doing this for a while modeled what it looked like. And the first day I sat down and watched a very technical piece of instrumentation that I would teach about be completely taught through active learning. And it was like, my mind was blown. And I was like, this is how I want to teach. But I didn't know I could do it until I saw it being done. And so that's what I want to kind of model for you a little bit today. Now, our traditional classroom usually goes with lecture. They might practice a little bit and then e-learn after, some homework, some kind of follow-up, formative assessment, summative assessment. And then you've probably heard of a flipped classroom, which kind of flips it backwards, where they're doing some kind of learning outside of class, and then you're doing almost exclusively practice in class. And it is really hard to go from one to the other to completely flip your own mindset. So what I want to do today is give you middle ground, where you don't have to rethink your entire course into a 100% flipped classroom. You can rethink sections of material and things you're already doing, maybe that you talk through, into students talking through. And this is how I tend to run my class. I call it a modified flipped or a blended active learning. I have a lot of terms I use for it, where I do mini lectures and then they have some time for group work, and then mini lecture and then some time for group work. So I want to make sure you kind of see that this can happen.
Can we take pictures of your slides? Are these?
Yeah, and they're going to be available as well.
Okay.
I think Brad's going to send out that and the handout today. So you should have all of this available. So specific goals for this TLI, we're going to demonstrate learning with active learning techniques. We're definitely going to do some terminology, some calculations, a little bit diagram, data interpretation. I've got some create or design questions at the end if time allows. We'll see how well we're doing. And along the way, we're going to pause and kind of discuss pros, cons, some additional methods that I might throw in that I don't necessarily have an example in the handout for. So everyone ready to participate? We're good? All right. You don't just get to sit and listen to me today. All right, so the theme for today, okay, is all about light. And again, I come from a chemistry background, but we're going to kind of start and ease our way in some things that I would bring to my like introductory chemistry, non-majors. You don't have to know science, but we're going to start at the basics and work our way through a variety of things that all kind of revolve around light and how we use light to make measurements. So go to your group handout, okay? Now on your group handout, you'll notice a few things. I always start with student learning objectives. So at the end of the day, when students bring this handout home and have it to start studying for their exam, they know what I expect them to pull from this handout. And it's kind of all embedded throughout. So there's not going to be like, oh, I have this checklist review sheet, but that's kind of my review sheet for what they should know. If I had associated reading, like, whoa, we're in chapter 5 of the textbook, or there's a article that I posted online on Blackboard, I would have that there. And then, oh, there's this homework set that's going to use this kind of material. So make sure you go do that. So I always put those kind of at the top. But we are going to start with the discussion questions. So go to your groups and you're going to do some brainstorming about the kinds of light you know about, and start thinking about how the light's used and what kind of energy it must have. Okay, so we're going to spend just a couple of minutes on this. So kind of take a deep breath, start embracing your light, think about light, and chat with each other for just a couple minutes. Okay. And if you're on Zoom, please chat with each other in the chat box. This is still interactive, even on Zoom.
X-ray. Yeah.
But I don't know what, I don't know what part of the day. I have something that makes but I don't know what.
Part might be is it like this light, or is it more like the ultraviolet?
I'm guessing it's not.
Kind of
Like this, on like side. Well, that, no, that's.
Yes,
There is something.
but that's an application of light, and there are a lot of shades. So it enhances our visualization.
I thought that was representation.
Oh, and then they make. You know, the ones that eventually uses your arm.
Yes.
Is that not like?
We have a question about medical.
Okay.
What type, like if you're doing X-ray, MRI, CAT scan, what, or are those light percent?
Those are light, they are
Okay.
different parts of the spectrum of light, so
Okay.
different energy. So
Okay.
an X-ray, you can find an X-ray like, oh, we don't need to have too many X-rays. Yeah, we usually, that must be like, there must be something different about that light than like an ultrasound, which they're like, well, ultrasound, you already have your pregnancy if you want, you know? Like, I mean, you don't, in terms of pay for it, but, you know,
Okay,
they wouldn't have a medical qualm about that,
okay.
you know?
But you said they are all types of lights?
Yeah, they are, well, okay, so ultrasound is not, ultrasound is actually sound waves, so.
Okay, that's
But
what I was
X-rays,
X-rays.
I think MRIs uses magnetic resonance, so it's
These products.
it's similar to light, but it's maybe not quite the same. Because MRIs don't have the same power of an X-ray
X-rays.
in terms of biologicals effects.
And then when you.
But some of the cancer radiations are using kind of like laser pinpoint.
Yeah.
With light.
Yeah, like, you know, for cancer, sometimes they have the proton therapy, which goes specifically.
One, and proton therapy would be using protons rather than photons, which are
Photons.
yes,
Is that with an F or with a PH?
pH.
I like that name.
Yeah.
All right, so if you, yes, Brad.
We had a comment online on shoot.
Oh, excellent.
Benjamin said, what's the best way to encourage students to participate? I'd rather sit there and observe.
I walk around to tables and I ask specific students questions. I look at them very squarely and I say, what are your thoughts that you're bringing to the table? Like, what are your thoughts on that one? It helps if you have a small enough, group of students that you know all their names, but even if you don't know their name, you can stand there and go, and you just walk over and you're like, hey, can you summarize what your table's been talking about? Because even if then they don't have to get their own ideas, they actually are like, oh, I haven't been listening, and they kind of look around for help, and then someone was like, well, remember we were talking about this, and like, oh yeah, and this something, you know, and then they know that they're going to be held accountable. It only takes once or twice to do that in a room of people, and everybody knows you're going to do it. Students learn real fast. Okay, if you haven't moved on to the question about energy, let's go ahead and shift that way just so we can keep moving forward, because there's lots of light. We could spend the next several days brainstorming light.
Yeah, the sun has a tune.
Well, you know.
Is that say like the X-ray or? Well, no, that's not probably a light bulb. Yes, because there's the savers. Yeah.
Star Trek is not faster than third of flight. Or one, or is there? There's eight, but.
That's a little outside of where.
I had a book called The Physics of Star Trek once.
So, you know, we cheese them to say when we choose, so they have.
Oh. Oh.
The Star Trek
Yeah, or maybe the energy. Yeah.
All right, let's take one more minute on these light questions, these first couple.
Light or no, because it's coming technically from like the sun or a light bulb. Would reflection? Would reflection be? Because that's technically coming from the sun.
It's not, it's not a generation.
Okay,
So typically just redirecting what's already. It's a property of a material in regard to how.
Radio waves.
All right, so as you're wrapping up your energy discussion, let's go ahead and throw out some of the types of light that you might have experienced or thought about. So what are some types of light? And we'll kind of start building a little bit of a list of maybe some of the different ranges.
Are we just supposed to yell?
Yep, just yell.
Sun and the moon?
Sun and moon, okay, so the moon is reflective, so it's not generating light, but the sun
Like you just
is
said.
gonna generate light.
Yeah.
And we experience that mostly as kind of visible region light. What other places do we get visible light? That butter's not gonna fly today. What are some other ways that you found like visible light that we experience on our daily basis? You guys were talking about, like light bulbs and.
Yeah, light bulbs, yeah, the lights in here, light bulbs, indoor lighting. Fires, come on.
Our cell phones and their blue light.
Where the common chat said lasers.
Lasers. Some of those are visible, right? They tell you, get a little cat toy that says, don't shoot this in your eyes, right? Okay. What are some other types of light besides these kind of visible things? How else do we interact with light?
Listen to the radio.
Listen to the radio.
Watch talk radio.
And that is actually carried using light waves, okay? What else?
Microwave.
Microwaves. The kitchen appliance is actually named after the kind of light that it uses to heat up your food. And it does tend to have a little visible bulb so you can watch your food explode. But, you actually are using microwaves for your actual effective heating. Any others you thought of?
Heat is another one in the comments.
Heat. So heat is technically different than light. It's often emitted at the same time as light, or the light can have an effect of warming something when it interacts with a matter, with solid matter. But it's not technically light itself, but that is a really good kind of pairing. And when we think about things that happen together, that's a really good thought process. I'm going to throw one out. This one gets me every summer. Ultraviolet. I burn and I burn and I burn, and then I freckle enough that I look tan. Okay. What else? Anyone broken a bone? X-ray.
What about gamma radiation?
Gamma
Incredible.
radiation. I'm gonna put one more up there. Heat, or like night vision goggles.
Oh.
Use IR, infrared. Okay.
And we use infrared for remote controls.
Yes, we can use those for remote controls as well. All right, so we've got like 7 different ones, and this is broadly what the actual spectrum of light is broken into, is kind of these 7 categories. And many of these we've experienced in one way or another. We've heard about it. We kind of didn't maybe piece it all together, but what we're going to do next is, if you flip the page, the next couple questions, the first one deals with saying, okay, which ones do you think have the highest energy and lowest energy, which we're going to kind of work through together as a class. And then the next 2, you're going to look at some specific terminology associated with light and what makes each of these different. Okay, so just by our own understanding, which one of these do you think is the most harmful if we were to come into counter with it? Gamma rays. Okay, we use this for cancer treatment because it just kills cells. Okay, so this is going to give the most damage to us. This is kind of how I think about what has the most energy, because it can cause the most damage. Okay, so gamma rays are going to be your first kind of highest energy. Okay, what do you think is next? Do we have a vote for the next one? We've got a vote for X-rays. Anyone want to second that?
Well. Ultraviolet also.
Okay, ultraviolet, those are both ones that we don't want to come into contact with a whole lot, right? We are warned against sun exposure. We're also warned if we go to the doctor about not getting too many X-rays, right? Both are going to cause cancer. The one that is actually more detrimental to us are the X-rays. And so when X-rays first started being used, they kind of warned and said, or they were using it for everything. And then all of a sudden it was like, oh my gosh, we can't use this for everything.
And mercury, died of cancer.
Exactly. So X-rays are second, ultraviolet is third, kind of going from most to least energy, okay? And then ultraviolet, where do we go from ultraviolet? Okay, that's a good guess, and that's a lot of that is because we're not as familiar with the effect. We don't just get to stick our hand in a microwave, right? Like that's not really how we roll. But actually, if this is the way I kind of think about it, ultraviolet has a color in the name, and so does infrared. So they kind of straddle the edges of our visible light. So we go ultraviolet, visible, infrared. And then our last two are actually going to be microwave and radio. Okay, so that kind of gives you, so if you're working along on your sheet, kind of from left to right is number 1 to 7 on your little chart for number 3. Okay. So the next 2 questions, number 4 is really going to look at some terminology. Number 5 is going to then have you consider some scientific units. And I know we haven't talked about scientific units in this class. So if you get stuck on that one, don't panic, okay? But just start to kind of think about science. Usually I would hit light after we've already talked about basic scientific units. So if that makes you panic, please don't. But so go ahead and return to your groups and do 4 and 5. And when you get to the spot that tells you to stop, stop.
There's your little table.
Right, so this is all the same. The difference between trust. Yeah, the graph is my thing. Like, compliments. Now, when we get to the next part, the graph is the number of ways that. Just be like the number of closely. We haven't said this in our course. This one is being so these are split press. Number of ways has press. Yeah. This is. Yes. Oh, that frequency.
Or something.
No, we just count that by.
The frequency is how. So if it is for the up or down. How do you make the yeah. Oh, I was just.
I just want to make sure your arrow goes up, down versus.
And then
up,
this is
up.
the number.
And then wait.
But to make them
Yeah.
a smaller number, you need more.
Yes, that's one spot, same spot.
Oh, and they have close to it.
That is one way to look at it.
Yeah.
I know,
Yeah.
it's weird me out.
Oh, yeah, there was. Okay.
Yeah.
Now I'm just remembering things from college.
And what's new?
Are related to each other. Yeah, because.
There you go.
We learn how they are related.
Excellent.
Well, we draw them the same way, so it's like, wait, what? Like, how can you draw this, you know, we draw them equally, and then they have to relate. So we couldn't make more rings, like, less waves.
It depends on how fast they're moving, right? And so we draw it out of, and then we have to know what the scales are.
Well, we couldn't make them,
Just like.
less frequency without making them farther across.
But then your wavelength is actually different too. So if we're dealing with the same speed, then yeah, frequency and wavelength have that kind of inverse.
Oh,
Faster frequency. Oh, speed, what is speed? So it depends on the speed. So speed, I didn't have you assign. If you go to the next one, then we get to bring speed with the frequency and the wavelength. So you were already talking ahead to the next part, which I love. How's everybody on Zoom doing? Get through the first question 4. Brad, is there anything in the chat I need to address? No, they're just chatting.
You know, one.
Somewhere in there. Frequency would be.
Oh, he says.
Well, the
That-
speed of light and the.
Oh,
units. So I think it's. Second.
Oh, you're right. Hold on. Meters per
Wait,
second over-
What is?
It seems like you know where you don't. It's not, you can figure the graph away. Right, this ones we got with the graphs, but this one's easy that you know whether you don't. I feel like.
Well,
You can guess it.
no, so if we're talking about wavelength, we've defined that as a distance, what kind of units would we use for?
Meters per second.
Like
Over.
feet.
Meters, right? So some kind of like that, and then you look at your speed of light, what kind of units are in there?
Yeah.
We have meters, which is a distance, and then we have a seconds, which is a time. So what kind of units must our frequency have? It must be us.
It's time.
Okay. So, and then you gotta look at, okay, are they in the top of the fraction, the bottom of the fraction, how are they using out? What do our units end up being? So it's a little dimensional analysis there.
I have a question about, and you might get to this, so you can tell me if it comes later, like, what do you do if students don't show up? Like, obviously, I'm not prepared for your class, so what do you do with those students?
Like if they don't come prepared, if they don't come prepared,
Okay.
like they don't come with like a scientific background.
Or they haven't, like, if there was pre-reading or something like that.
So I don't assign a lot of pre-reading,
Okay.
but if I've assigned something, usually I have to make them watch a video. And then it's track on YouTube, the videos sometimes reviews don't correlate. They were talking about video like 10 out of my 30. That, and they say, well, congratulations, we are skipping this entire section and you are now responsible.
Yeah.
Onto this next topic, and I've done this stuff. And then they went, they're like, oh yeah, we as a class, because I need at least 1 or 2 people at each group of 4 to know what they're doing. Right? So I do that, and then and then I usually post when we are finished with the entire set. I will post the answer.
Yeah.
Okay. Oh,
So they
don't
don't have
have
to
right.
refer to it. But so, you know, stop
Yeah.
a session and then we might carry it on the same handout for a class
Yeah.
period, and then they're like, then they know to just talk to me.
I think that's right. I think
it is.
All right, everybody kind of comfortable a little bit with your units? Okay, we've done some definitions here. We've defined our wavelength between the crests or the troughs. We've defined our amplitude as the height, and frequency is hard to define on this specifically because it is based on kind of the speed at which it does go, right? Which we then get to look at in question 5 when we introduce, you know, frequency related to wavelength using a speed, okay? And I did have a comment that, you know, how are we supposed to know? I mean, you already know it when you come in or you don't with those dimensions, but I want to point out how we can get there without having known anything, okay? So we have our Greek nu, which is like a V with attitude. And my chemistry professor always would say, as soon as she introduced this, was like, what's new? And the answer is C over lambda. And from thereafter, almost every day she would walk in and she'd say, what's new? And if you didn't answer C over lambda, then she would make you say it again until everyone in the class knew it was C over. So I'm like, this is like forever ingrained in my head. Okay, so we define wavelength, right, as a distance, a measurable distance. And what kind of units do we use for distance? Meters, that's our scientific unit. Now, some people throw out feet. If we've already covered scientific units, students should in the class previously, then they should be able to go like, okay, meters. Meters is our thing, right? So we might be in meters. And I gave you units here of meters per second. So we have meters per second over meters. And so we can dimensional analysis our way through this, right? So this is the same as saying meter over second times 1 over meter. Our 2 meters cancel, which leaves our frequency is going to get seconds, but they're on the denominator. So it's like an inverse second, okay? We also call this a hertz. not the car rental company, though I think they kind of stole the name. Okay, but this is a Hertz. Okay, so we've got that going on, and I think. Okay, so we got through that to here. Okay, so now that we've established this equation and everything, we're gonna do some math. And I did not require everyone to bring a calculator. So and I'm not providing, but this would be the opportunity, okay, where I would take students and give them a chance to use this equation with our actually plugging things into their calculator, because Lord knows calculator errors are everything, especially when you do anything in scientific notation. And then you divide things that are scientific notation, and it never ends well the first time. So let me just kind of talk through this next section and how this would run, though we're not actually going to do it. Okay, so we're on question 6, 7, 8, and 9. We're just going to do this whole section. Like, I'm just going to talk through it. So the first one is simply taking this straight up equation here for frequency and wavelength together. And I have 2 examples here. And what I would have students do is to start with the question. I would split them up into, in their groups. They're each going to get a question. So I have 2 groups here in my room today. One group is going to get the question A. One group is going to get question B. The calculation that they're doing is exactly the same. They just have different wavelengths. Okay, one of you gets red light, one of you gets ultraviolet. Okay. And so what happens here is that the students are practicing the exact same skill, but they're going to have obviously different answers. And so when they kind of report out their answer, then there's more examples in the room than me working one example and saying, and it works the same for any wavelength you want to put in there, right? Also, I think my wording, which I changed since I printed my instructor copy, has the students then, once they get it on theirs, then they take their answer and go share it with another group that did the other question and kind of swap their answers. So they should have both examples in their handout at the end of the day. And I would circle the room and kind of make sure that all the A groups are getting the same answer and all the B groups are getting the same answer. And we sort through calculator errors. And I probably would have prefaced the calculations with a, don't forget about, using parentheses in your calculator and all the things that we know lead to calculator errors. So at the end of question 6, they should have, multiple examples of how to work the exact same problem with different numbers putting in. And then they can use that correlation between red light and UV light, which I already gave you your frequencies there at the end of the question, what the answer should be, to then answer 7 and 8, which then say, okay, if I've given you 2 different wavelengths, one's bigger than the other, red light has a higher wavelength, 700 nanometers, ultraviolet is 300 nanometers. What is the relationship between energy and frequency and energy and wavelength? Okay, so they have the wavelength that I gave them, the frequencies that they've calculated, and we've already put them in order of which ones should have the higher energy, right? Ultraviolet has higher energy than anything in the visible region like red. So we should be able to come up with, well, if it's a higher energy ultraviolet, now it's got a lower wavelength and it ended up with a higher frequency. So now we've got these kind of correlations together. Okay, so we've got a numeric punch it in your calculator example that leads to a correlation trend that I want to observe that builds and ties back to where we started with our discussion and something that they experienced in their daily life. UV versus violet. UV burns you, higher energy, red light, I'm okay with, right? So that's kind of how I approach some of these math problems where I want them to be able to work this calculation 8,000 ways and not run into calculator errors. But I don't want to do 8,000 examples in class. Okay. So there's my little answers. You'll get these slides. So this is the kind of way that then they kind of get to build their little table that if you just put the numbers in that we calculated and determined, then we can see that those have a relationship. And so if all of those have a relationship, there must be an overall relationship between energy, frequency, and wavelength. And that builds into the next question. And again, all of this they're doing in groups, so I won't stop the class to do any of this kind of summary. They should just be summarizing as they go. So the next step is then they get their energy equation here, and they're going to redo their red or UV, depending on which group they're in, and this time calculating its energy. Okay, and what normally happens is one student decides to start with the wavelength because that's what I gave them in the question. And inevitably, someone at the table recognizes, well, we've already calculated a frequency, so we could just use the frequency version and they'll come out with this, they should come out with the same answer, right? Because it's same numbers. So it kind of leads to that ability to say, okay, I can do it either way.
Yeah.
Okay.
If
Yep.
those groups, like if any of them are like totally off, like they're totally wrong, like if I was to step in your classroom, I haven't done chemistry in 20 years. What do you do with them? Do you like stop them or do you kind of let them come to their own conclusion since they're
So this is where a group dynamic tends to work, because what happens is there's usually somebody at the table that's like, oh no, I'm right. And they're usually right, okay? But then there's occasions where the person who is completely off base thinks they're right, but that's where then you compare to other groups. And as soon as they stop and compare to another group, and the other group's got a different answer, and someone at their table had that answer, and then usually I get flagged across the room, they're like, Dr. Tran, what are we aiming for here? And so, and oftentimes if somebody is getting a very different answer, then everyone kind of pours over and goes, well, what are you doing differently? Is it in your calculator? Is it in how you're setting it up? Did you put the right numbers in the right places? And as I'm circling the room, I can hear that. And I know I'm like, okay, I got to go stop at that table because they're not in agreement on their numbers when they should be by now. And so something's going on there, and it could be a calculator. It could be I've got the wrong equation. It could be I didn't convert my units. Okay, which is about where we're at for these.
What would you say is the upper limit of the size class in which this is still functional?
So I've done this with 30 students. And that's about as big as I've done it. I think you could do it with more than that, but I might make the groups maybe 5 or 6 students at a time instead of limiting it to 4. I think 4 gives the best balance of amount of input without letting somebody just skate by and not do any input at all. I think if I were to have a class, I know, Ben's teaching a class of like 100 students in Chem 1 right now, and Lord knows that's not something I've been asked to do yet. But I've actually done these kinds of things on Zoom with a document camera with students and put them in breakout rooms and had them come back, and it's more time consuming. Yeah, it's hard to circulate if you've got more than about 8 to 10 groups. And even then you're not going to hit every group, but that's where building in things like telling them to find another group that has their same problem and putting those kind of in the same space of the room is when you're correcting one group, another group is always overhearing. So, if all of my A's are in one corner and all of my B's are in another corner, then you're correcting one B and someone at the table knows that they now have the right answer and it spreads. So that's usually how I find it working. The more groups you have, the more they over listen. If you're anywhere in the vicinity, they're listening to what you're saying. Okay. Other questions so far? Yeah.
I do. As normal, I am teaching classes that I have never taught before and I'm not an expert in.
Mhm.
What do you do in that instance? Like, there are some times where I am not gonna be able to take information. Like, if they ask me a question, I just literally don't know. What do you do? Like, here you seem like an expert and just can.
Yeah, so one thing that I found is, especially in teaching classes the first time, building handouts is by far the fastest way to anticipate what the student questions are.
Okay.
And building your answer key at the same time you build the questions.
Okay.
Because what that makes me think through is really what is the logic, what am I trying to get at, and what is the logical order to get them there?
Okay.
someone's always going to go astray somewhere that you really didn't anticipate.
Yeah.
And then it's about being like, okay, that's an interesting sidebar,
Yeah.
but let's bring it back to this part of the discussion.
Okay.
Let's focus here. And it's a little bit of redirection, you know, and especially in micro levels, I'm really honest. I'm like, hey, that's not something I'm not an expert in that. I could go look at it
Yeah.
and we can bring some information back.
Okay.
That's what I usually say, and that happens to me all the time. They'll ask me something, I'll go, gosh, that's a great question. I even have a designated student who will text me the question. So that way I can look it up and not forget to look it up.
Usually I've been making them look it up and report back in that.
Oh, I do that too. Look it up for me, please. Yeah, if they Google it, they can, yeah, because I said, you know, like, how do you think I'm gonna go try to find out the information? I'm gonna probably Google it.
Mhm.
Okay, thank you.
Okay, so kind of, Brad, what time are we done at? I don't want to go over on time, but I think I'm getting close to time. Okay, so kind of continuing on this, now they've calculated energy out and they can kind of finish out their little table there that shows them very clearly some trends with that energy. And then the kind of final questions in the section before I would have them stop and we kind of regather to make sure everyone actually got this table and these conclusions. Ask them to then apply it to a microwave frequency. So they would basically then just kind of go back to their table and say, oh, where does microwaves fall? I think I have that written under radio. It should be under microwave. I will fix that. It's in Google Drive, so if you have the link, it'll fix itself.
I like how you put the stop signs on there. I don't normally do that.
Yes, I didn't initially, and I'd be like, let's just go to somewhere here, you know,
Yeah.
but that makes me know where are my stop points? What do I expect them to cover?
Yeah.
And then the next spot is usually a room for notes, which means we're moving to like a mini lecture.
I have some students that will just,
Keep going and going and going, and then they've done the whole handout and you're
they'll
like,
do the whole handout, but they won't really do it
mhm.
well. And because they're rushing.
They're focused on finishing everything and not thinking through, and that gives them a stop point. The week-long intensive that I had done had some follow-up sessions like 6 months later and a year later, and that was some feedback I got on my handouts at the 6-month mark, because they were like, or someone else had done it, and I was like, that I need that. And I used to have a little stop sign, but that takes up too much space.
So wait, what do you do 6 months later?
Oh, so I did a week-long intensive like workshop on active learning and analytical chemistry. And as part of their NSF grant that hosted this, they had a 6-month follow-up for everybody. So we all, yeah, for me, for my, no, yeah, not for the students, sorry. For the faculty that went through the program to help us to come back and be like, okay, well, what are you doing and how can you make it even better? And that was feedback that came out of there. Okay. So we've now hit kind of our room for notes, and I've got a couple of thoughts on this kind of terminology and calculations part. Just things that I found have been useful is, especially when you're adding new terminology, if we can build on an already understanding or already experiences, that really helps. Lengthy math problems, always scaffold, because then it makes it really easy to know what step did they go wrong on. I have this one problem in an upper level class where the equation includes square roots or squaring things and then adding them together and then taking the square root and then divide by this and add this other thing. And in unit changes along the way. And so there's always issues, and that lets me know, oh, well, from step A to step B, that's where your number's wrong. We can fix it there. So scaffolding is perfect. Providing clear terminology and definitions. I don't like to have students generate a definition because then they don't have the right definition. I would rather try to do something where I can give them the definition and have them do something with it. So when they take their sheet back, they have the clear definition already in their notes. When you do, this is like personal pet peeve, but using wording and styles of questions similar to what shows up on the assessments, which can be hard if you're using like a textbook e-learning system because you're not writing those questions. But if you can mimic some of those stylistically, it helps students go, well, this is just like what I did in class, and now it's showing up in my homework, and that's how it's going to show up on the exam within reason. But they know how I ask questions and how I want them to think through and answer the question. And they start trusting that when I give an open response question, they do have what they need for it. so they don't panic when they hit short answers on my exams. And again, that kind of maxes out at about 30 students. I've done short answers on exams with 50, and the grading is intense. I don't recommend, but I do recommend because upper level students really do need some short answer questions. So it's love hate. I like this using multiple similar examples spread across the groups, but being really strategic in how you do it instead of just saying red light, red light, red light with slightly different wavelengths because there's a range, but being like, okay, what's the next thing I want to cover? What's the next trend? Or what's a trend, maybe 2 or 3 sections down the road that I'm going to want to come back to and be like, oh, we've already investigated this, maybe in the introduction of elements, I give each group an element, but I'm already thinking about, well, when I do periodic trends, so I want you to have different elements that are going to eventually show me the periodic trends. And then you're like, oh, well, we looked at this element and you looked at that element, and now we're going to bring those together again. So kind of being really strategic with the foresight. And then sometimes you have groups that work really fast, that just like, we're good, we're done, and everyone else is still like 3 things behind. So I usually in my first iteration of a class, I don't have these because I'm still building as I go. But by the second or third iteration of a class, I usually have challenge problems at the end that are just kind of extras. So I might take this equation and give them frequency and make them calculate wavelength, or some additional food for thought things that I might have written in and then found we just spend too much time, we get bogged down in that. So here's a challenge problem at the end. And so they can go back to them in their own time, or your super quick classes can just like, you're like, why don't you try a challenge problem at the end instead of trying, and then they're not tempted to blow by my stop signs and keep moving, because you're like, I don't want you to do that. I want to keep the class together. Or I will break them up and say, great, you got the right answer. Why don't you go help that group over there? You are now an ambassador. You get to go help another group, make sure they get to the right answers, but you can't just give them the answer. You have to explain it to them or help them troubleshoot it. So I do that sometimes too.
Are they receptive? Are they receptive of that?
Usually, yeah. What I don't want to have is the students then sitting there talking about something completely off topic for 5 minutes while I'm trying to finish the rest of the class up, because that makes everyone around them really annoyed and more likely to get off topic. But they become very used to that. Like once you do it a couple times, they kind of expect it, and it's usually the same group every time that gets done quickly. So
Do you give them full freedom, or do you do anything to kind of set up the groups in a certain way?
So I do somewhere in the middle. I officially assign the groups, but I usually wait till a couple weeks in, and the first couple weeks I make them sit at different tables and tell them they have to sit with at least one person they've never sat with before. And then at the end of the first maybe 2 weeks or so, I will ask them to give me an index card with the top 3 people they'd like to work with, and what table in the room they'd want to sit at. And I say, I can guarantee you one of those 4 things. I cannot guarantee you any more than that. So sometimes students get the table that they want to sit at. Sometimes they get people they want to work with. And then I kind of look at things like, you don't want to put people that tend to sit together and get off topic together. So you split them up in groups. You don't want to put the people that are going to just like bowl over everyone else with people who don't talk. And so by 2 weeks in, I kind of have enough notes to make some of those decisions. I also try not to put my super high achievers with super low achievers, kind of on incoming GPAs and where they fell in the prereqs. You kind of get a feel for that, because they will feel like they always have to defer to the other person. There's been some studies that show if you pair A students with B students, the B students come up. If you pair B students with C students, the C students come up. If you pair A students with C students, the A students stay put, the C students go down. So, and I can't find that one again, but I remember it like being in a heavy discussion. So always trying to kind of mix them up. I also don't like to have tables where it's 1 female and 3 male, or a minority with no other minorities at the table. So there's all kinds of that. It takes more energy than it ought to, but it usually works pretty well.
It's an art more than science.
Right. And then I have them do a group contract, because there's usually a project too. And it makes them talk through their previous group experiences and what was good, what was bad, and how to avoid the bad.
So are you doing this during lecture or is it
during
class?
lecture, during
Okay,
lecture.
very
Yeah,
much.
this is my lecture class.
Okay.
So again, there's trade-offs to doing all of that in lecture, but I feel in terms of the long term, the kinds of discussions we get, we do better. And the group contract also addresses if there's a problem in the group with the dynamics, what do we do about it? At what point do we call in a Dr. Tran as a mediator? At what point is a person no longer part of the group? And we all agree on the terms of that from day one as a group. And then I can just like enforce their contract that they wrote and signed. So
Would you be able to share?
I can share this. Brad, I'm gonna ask about time again, because I can't remember if we end this at 1:20 or 1:10.
11.
It's 1:11 and we're supposed to end at 1:10.
You can go with 9.
9 more minutes. Does anyone have anywhere they have to be? Yeah. Okay, so I'm going to kind of breeze through the next couple things. I wanted to do these all together, but we'll just kind of breeze through. Keep hitting the button. Sorry, everyone on Zoom. It's like getting something up there. Okay, so next we would move into some diagram interpretation, and I would come back to light, and now we're going to dive into a little bit more visible, and I'd say Roy G. Biv, colors of the rainbow, right? And we know from our discussion of infrared and ultraviolet, we probably have violet at higher energy than red, and we can kind of make that jump. And so we can introduce a little spectrum here that gives how violet fits in versus red here with those high energy, high frequency, low wavelength on the violet end. And then I would introduce a spectrum. Okay. So, and this is where, and students have now had two kind of like quick and easy warm-up questions. And now we're like, here's some data that we're going to do some interpretation on, and start by labeling violet versus red, which they've just decided which one's high wavelength, which one's low wavelengths. We're good. And then we talk about a little bit more challenging questions there about what wavelength has the highest irradiance. They should look at it and kind of, oh, okay, we got to go high. Where about is that down? Give me a good estimation. If they say 400, I'm saying you're not reading your bottom of your graph specific enough. You should be able to get a little bit more specific than that. You know, we can make those kinds of discussions. And then what other regions of flight are present? I haven't told you what the cutoffs are for UV and IR. We know those are the next ones on either side. Where do they cut off? And now I'm going to tell you to Google it. You know, you can look up that answer. You can find some information yourself and get used to. I'm not sure, but I know where to find answers here. Okay. Yeah, go ahead.
Do you direct them to like a specific website since there's a lot of stuff out on the internet, or?
No, usually though, we've talked a little bit about what makes something scholarly
Okay.
versus not. And so I might say, you know, look for something with an .edu at the end, versus something that's just a blog or a picture, or something that looks like it comes from a textbook, or, you know, or I might, if we were getting to the end of class like we are today, I might say, oh, take that home, look that up in your textbook and bring that back to us next time, you know. And then the part C that I actually really like here, we've got the ozone layers filtering out wavelengths from 200 to 315. So it's down here. I think this is actually cutting off some of our spectrum here, but it should filter out a little bit more than that. And so having students then redraw the graph on their group boards, and they would kind of show each other the boards, and we can kind of wrestle with, well, why did you draw your cutoff there? Why did you draw it here? You know, and kind of making those kind of one step further than just interpret what's there, but now predict how it would change if we have these circumstances change. And we spent too long on the initial lights to get there. And then we have another set of data interpretation here that shows the sun versus some other kinds of light sources in the visible region, and make them kind of wrestle with, well, which one is the most similar to sun? And that's always kind of a fun exercise, because, you know, you can make the argument for fluorescence or incandescence. You really can't argue for the helium neon laser, but then we can talk about, well, why does some need to have just a narrow wavelength? So it opens up some really interesting parts there. So a couple of thoughts on the data interpretation. I'm sorry, I'm kind of running through this. I wanted to do more active, but you know, giving enough information to reason with the question is important. Sometimes I feel like I give them a graph and I don't give them enough information because I want them to reason it all out. but you still have to give them something. So finding that balance and let them know when it's appropriate to use outside resources. I had one activity that I was doing and they had everything that they needed. And one person in the class was like sitting there on his phone and I was like, get off your phone, buddy. And he's like, no, I'm looking this up. I don't understand how this thing works. So I'm looking it up to read about it. And I was like, no, you're supposed to logic this out with what you already know. And he was like, but I can find an answer. So make sure that they know when I want them looking outside versus when I want them looking and building off their own. And I like to build some low stakes or kind of easy questions in. So they build a little confidence before, you just like, you're like, and now predict a new graph. Well, no, let's label it with what we already know. Let's talk about what we already know. And now we'll build some confidence with it. And then I like reporting out, making them draw their answers up on a board and then they start looking around and they're like, well, what did everyone else do? How is mine different? And they will actually generally start the conversation of why someone's might look different than theirs before I even start that conversation. And I really do appreciate that as well. And it gives me a chance to, in real time, correct their understanding. The last thing I was going to have you guys do is do a kind of a spectrophotometer design. This is something I would do in my upper level instrumentation course where you've got a scenario. You're going to pass light through a sample and measure how much light passes through the sample. What kind of parts do you need? And they'll come up with, oh, I need a light source. I need something to hold the sample. I need something to detect it. And you can kind of, well, what's the rationale for each? What kind of things do you want from each of those? Kind of build that design. So instead of me drawing a spectrophotometer up on the board and going, this is a spectrophotometer, it has these parts, they've thought through, well, what do I need in order to make that? And then I have them draw their spectrophotometer on their whiteboards. And then I can move into like, oh, if you're making a different kind of measurement, how do your pieces need to change? And
Are these, you give these are the whiteboards for the
I
students?
give these to student whiteboards. If I have room in my room, I will get kind of the tall roving ones and give each one a big one. But usually I give each student one of these. And this is literally a sheet protector with a piece of cardstock, and it lasts about one semester with really good use between erasing, and some of them have full spots or just no longer erases, but it's super cheap and fairly reusable.
And then you give them markers.
And then I usually give them each a marker, and I give them one marker at the start of class. And I say, this is your marker. You bring it to class with you, or you don't have a marker, and they bring it to class. So when you're doing create questions, finding where they can create their own design before showing them the real design, that's kind of where I can put those in. So when I look at my lecture, I say, oh, I'm going to throw up this design. Well, how else can I do that? Can I make them generate it? Or can I tell them the order of the steps that occur in this instrument? And then they have to draw what the instrument might look like in order to accomplish those steps. Or if it's got a lot of terminology, I give them the steps in the diagram and I say, now figure out where on the diagram all of your pieces are, like name all of your parts based on here's your steps occurring. Sometimes I'll give them the diagram and then say, here's a bunch of slips of paper with steps that occur in this instrument, put them in the order that they occur. Those are all ways I've kind of taken these kind of more complex things and made them really logic out what's going on in them, as opposed to just saying this is how it's done. Always make sure, you're going to get an array of answers. You have to ask for reasoning and accept the reasoning and redirect reasoning. I watched somebody do something like that, and then the person it was giving had a reasonable answer, but it wasn't the right answer. And they were like, well, that's wrong. So let's move on to someone else who can find the right answer. And you're like, that doesn't do it for me. You've got that student's never going to answer a question again. So making sure you're supportive in their understanding where it's at and redirective towards where it could go. And then, often their designs can launch whole class discussions. So as I'm running out of time, some overall thoughts, things I really love about this is I can really get all of Bloom's taxonomy into class really well, a lot better than I feel like I can if I'm just lecturing. We get workplace skills that I really want to make sure my graduates have. I can ask some deeper questions and hold them accountable without having to grade short answer questions all the time. And then I know it's their work because they're not, they can't use anyone else's thoughts because they're standing there telling it to you. And it allows me to see misconceptions as they occur, not after the fact. And I don't know about you, but I don't know if students read my feedback when I write them on their homework. So, yeah, if I can give them feedback in real time, it just nips it in the bud real fast. And also sometimes their classmates actually correct their misconceptions before I get to, and that's even better because then it is just generally good for the student doing the teaching and good for the student doing learning.
Do you give like participation grade every day?
I-
Or is it just?
I
based on
usually
your-
have participation. I tell them that their expectations that they participate when they come to class. They're allowed a certain number of absences before I mark off any on their participation grade because things happen and I don't want them to come in sick. But I say, if you are here, I expect you to participate because I don't expect you to show up to your job and not do it. So treat this like your job. You showed up, you're going to do it. If you're not going to do your job, don't bother to show up and take the hit. And I spend the first day setting expectations, and that does a lot. Some cons, it's really time consuming. We ran out of time today. It takes a lot of time. It means you do have to do less material coverage overall, or you have to move it out of the class to videos that they watch, or be like, you have to do the reading. Group dynamics can be, it's time consuming to create good handouts and to think through that logical progression. It takes some iterations to get really good at it. And if you as a facilitator are not 100% sold, it doesn't work at all. And then some final tips, but I think we've covered most of these as we've gone. So I'm going to just say, if you want to move forward, you want to have more conversations, I'm welcome to more conversations. And then faculty consultations, and otherwise I'll leave those kind of tips for success out. Good job. Going on. We're like, I don't know if I've had enough. So I always write more material than I ever need, which is why I like my handouts are usually multiple sessions. So.
How do you you're in analytical chemistry, so that's a much larger field than dairy science, but how do you find other people that, I can't think of anyone in my field that is doing active learning, and I would like to do, I cannot stand listening to myself drone on, and I know the students are not.